Welcome. This is question number 4 now for AQA's AS Physics June 2013 Unit 1 past paper. Now 4A says explain why the we're given the frequency. Basically we've got a photoelectric effect question. So what I've done here is I've drawn a surface of a metal with, obviously these are electrons, and we've got a frequency and a maximum kinetic energy of these. So obviously, basically we've got this instant light, so this isn't drawing of a photon, this isn't perfect, but I get into drawing a photon and we'll be here all day. And this light has a frequency of 3 times 10 to the 15 hertz, and when it hits the surface of the metal, because of physics, as I said, I've done a video on this, and basically we have these photoelectrons that are emitted. Okay, now that's not perfect what they probably would look like, but you get the idea. Right, so part A says, explain why emitted electrons have a range of kinetic energy up to a maximum value. Now, for this we have to consider, well, what is the kinetic energy equation? Well, the kinetic energy equation is EK, so it's kinetic energy, or KE, whatever you want to call it, is equal to the energy of the photon take the work function. And obviously the energy of the photon being equal to HF, H being the Planck's constant, 6.63 times 10 to the minus 34, and the frequency being 3 times 10 to the 15 hertz. Now, we could sub it in there and try and find out what theta, what I've drawn as theta, what essentially is the work function of the metal, but we're not being asked to do that yet. We're just being asked to explain why they occur up to a maximum. Now, this frequency we assume to be constant, so therefore each of these incoming photons is going to have an energy equal to E equal to H times the frequency. Now, we're not bothered what that is, we're not asked to work that out yet. Now, okay, so all of these, basically, these photons are transferring all their energy, we're assuming, to these electrons inside the metal. Now, each of these electrons are getting the same energy. Now, the reason is they're going to, what this essentially is, this work function, is the minimum energy required to escape the metal. So basically, it's the first layer of electrons to escape. That's the energy they need to escape, okay? So basically, when the energy of the photon equals the work function, then it just escapes. It doesn't have any kinetic energy, it's not moving, it just escapes the metal. But obviously, therefore the work function is going to be the same for all of these electrons, right? Well, yeah, because the work function says the minimum energy required. It doesn't say the energy required for each electron to escape the surface of the metal. It says the minimum energy. Now, basically these electrons have got, the ones at the bottom have got to push all these other electrons out of the way and spend energy actually getting to the surface of the metal, so then therefore they can overcome the work function and be emitted. So they've got this. Now, we'll see now energy is work done, and work done is force times distance. So they've also got force in to move this distance, which implies this energy, which implies this work done, which implies there's been energy transferred. So they must have transferred some energy they received from the photon, these electrons at the bottom, to push the other electrons out the way to get to the surface of this metal and therefore be emitted. So they've done a little bit of energy and work pushing these other electrons out the way. Yet they still need to overcome the same work function that the original electrons at the start of the metal, the start being the surface of the metal, had to. So basically, these lazy ass electrons at the top of the metal, they don't have to do any of this extra work, they just have to overcome the work function. But these metals have to get up to the top and then overcome the work function and then be emitted. Now, we have to go back to the question. We have to be able to apply this to the question, because I've just given you a bit of background. So the question actually says, explain why why the emitted electrons have a range of kinetic energies up to a maximum. Now, it kind of said these electrons at the bottom have to push to the top and then overcome the work function. Hence, they have to provide more energy. They have to lose more of the energy that they originally gained. Now, we're assuming the only energy that is so basically, when these electrons have escaped the metal, all their energy then goes into being kinetic energy, so movement. Now, obviously, if these electrons have had to use up less energy to escape the metal, therefore as we said, all electrons have the same initial energy. If they've used less to get out, then therefore, by logic, they must have more left over. And as we said, the only energy that's left over is transferred into kinetic energy. So therefore, the electrons at the top have a maximum kinetic energy. Unless the electron's already outside the metal, in which case this effect cannot take place, then that is the maximum layer of kinetic energy that they would have, because they're closest to the surface of the metal, don't have to do any movement to get out of the metal. All they have to do is overcome the work function, and then they have the maximum energy. Now the further down you go, the more energy that will be used up by the electron to get to the surface. Okay, so basically that's why we have the maximum, because the maximum kinetic energy comes from the electrons that are closest to the surface, because they don't have to get to the surface of the metal. So that's the key thing for part A. And I'll try to highlight it by drawing this rather crude diagram on the board. Okay, so that's your 3 marks there. So if you want, I'll just try and... so I give my explanation of it, and I'll just see the mark scheme's got anything specific. So the 3 points, so I kind of said it in a roundabout way, but just to summarise, the 3 points you need to have are the energy of the photon is fixed, and you've got to overcome the work function. So there are 2 marks. So you've got to have the energy of the photon is the same. That's your first mark, and then obviously therefore they all absorb the same amount of energy, and they have to overcome the work function, which is the second mark, and then a third mark if they're saying, okay, well, actually answering the question now, well, the electrons that are further down have to do some work to get to the top, therefore have to transfer some energy, so therefore they have less energy left when they escape the work function of the metal, so therefore they have less kinetic energy. That's essentially a quick summary of this answer. I tried to give you a bit of an explanation onto why we come to the answer, but that's essentially what the mark scheme wants you to do. Now, you could just look through the mark scheme if you wanted to know the answer to this question. I'm kind of hoping you're watching these videos to give you a bit of background, because I do think AQA mark schemes are quite nice. Now, show that the work function of this metal is 1.8 electron volts. Now, obviously, there's nothing that we can convert, so when we find out the work function, we find it out in electron volts. So we're going to have to find it out in joules, because all these are in, because the maximum kinetic energy is in joules. So we work it out in joules, and then we convert it to electron volts. Now, you could work out the electron volt kinetic energy to transfer that into joules, but you'd have to change that for the frequency, something else, and you just get yourself in the middle. I would just keep it, work it out in joules, and then convert it to electron volts after. And I'll explain how we do that in a minute. But the first thing we need to do is work out what the work function of the metal is in joules. Now, we're given everything else. So EK, we were told, is 1.7 times 10 to the minus 18. And this is a show that question, so you can kind of ignore the work function, the answer it tells you. We know H is 6.63 times 10 to the minus 34 times the frequency, which we are told is 3 times 10 to the 15. Sorry, I just put minus 15, yes, put 15. Take the work function. So it's just a case of simply rearranging that. So I'd do this calculation first, and then do whatever this is. So if we arrange this without doing any calculations, if you want to see how we get to this, but as I said, it's just a quick rearrangement. So it's the work function is 6.63 times 10 to the minus 34 times 3 times 10 to the 15. Take the 1.7 times 10 to the minus 18, and that gives you the work function in joules. Okay, so it's just a simple case of working that out now. So the 6.63 times 10 to the minus 34 times 3 times 10 to the 15 is what I first work out. That gets you 1.989 times 10 to the minus 18, and you take that away from 1.7 times 10 to the minus 18, so you put that as an answer, take away 1.7 times 10 to the minus 18, and you should get an answer of 2.89 times 10 to the minus 19. Or 2.9, I just leave it 2.89 times 10 to the minus 18. Now remember, that's in joules, oh sorry, minus 19. Remember that's in joules, so we've got to convert it into electron volts. Now how do we do that? Well, I always tell myself this little story when I'm thinking how to convert it from joules to electron volts. Now, the reason that scientists came up with electron volts, 1 electron volt is equal to the, well, as it says, it's 1 volt of electron. And that's the fancy way of saying, basically, it's the charge of 1 electron. That is all an electron volt is. It's just the charge of 1 electron. It's actually quite contradictory when it says electron volt. You think of volts and you don't think of charge. Well, you don't think of charge. So it is quite confusing. But that's just what scientists do. Just want to confuse you with stuff. So they seem smart. Hence why I'm trying to do this. Anyway, so basically what we're saying is if electron volts, basically joules are always smaller than electron volts, because remember 1 electron volt is 1.6 times 10 to the minus 19 joules, and that's a very small number. So if 1 electron volt or 1 eV is equal to 1 charge, 1 joule of 1 electron charge, then I had this right in my head before. Then 1 electron volt is equal to 1.6 times 10 to the minus 19. So therefore, electron volts will always be bigger in comparison if you timesed it out to get 1 apiece. Okay, so if by using that, you just think, okay, well, electron volts for scientists to look at really small things in a bigger way, but you'll keep it to scale kind of thing. So if electron volts are always bigger, and the electron volt is 1.6 times 10 to the minus 19, we're obviously timesing it or dividing it in comparison if we're going from joules to electrons volts or electron volts to joules. Now, which way around we do that is key. We're at joules at the moment and we want electron volts. Now, we said electron volts are always bigger. If we times this by 1.6 times 10 to the minus 19, this is obviously wrong by the way, then we'd end up with a much smaller number, because obviously 1.6 times 10 to the minus 19 is obviously a hell of a lot less than 1. So if this has got to be bigger than an electron volt, if electron volts have got to be bigger than joules, then we've obviously got to sort of make it bigger. And because we're dividing it by, we're doing something with a number that is less than 1, the only way of making it bigger is by dividing it by this number. So therefore, we took from joules to electron volts, we divide by the charge of an electron, which is 1.6 times 10 to the minus 19, which therefore should get you the work function of 2.8 eV. Okay, so hopefully that makes some kind of sense. If you want to double check that on your calculator. If this isn't working, I made a hell of a mistake somewhere. It's the answer. Sorry, one sec. I'm just double checking because I don't want to come out with this and be wrong. 6 times 19. Oh, sorry, is it? Oh, it's not 2.8 eV, it's 1.8 eV. I did the calculation wrong, but it's asking it to be 1.8 eV, which is what you get when you do that equation. Alright, so that's essentially what you do. Now, you could just simply remember to go from joules. EV is always bigger than joules. I can't explain why. And therefore, when you're going from joules to EV, you divide by a number that is smaller than 1. So therefore, you divide by the charge. So basically, if you're going from joules to EV, because EV is always bigger, you divide the joules by the charge of an electron, or if you're going from EV to joules, because joules are always smaller, you times by the charge of an electron, because that's less than 1, so you're making it smaller. Okay, so that's just kind of a bit of background if you don't know how to convert between the two. Otherwise, that was quite a simple part. And for you, I probably made it more complicated than it ought to be. Calculate the next part, 4b, part 2. Asks us to calculate. Now, this work function of the metal, by the way, that's not going to change. That's the work function of the metal, just like this is the maximum kinetic energy. That's not going to change. Okay, so anyway, going on to this actual next part. Calculate the threshold frequency of the metal, given a number appropriate to a certain number of significant figures. Now, threshold frequency. This obviously all depends on your understanding what threshold frequency is. Now, basically, what a threshold frequency means is it's the frequency, it's a minimum frequency, just like the work frequency, the minimum energy required to emit an electron from the surface of metal. the threshold frequency is the minimum frequency to emit a photon from the surface, a photoelectron from the surface of a metal. Now, they're very similar because the only difference between the two is Planck's constant. That's a constant, so it doesn't have any bearing on it. So you think of them as being a similar sort of thing. Okay, so even though they're worded completely differently, sound completely differently, the threshold frequency and the work function is kind of the same thing, and I can hope you can see that. Obviously, the clear difference is because one says threshold frequency, is one asking about work function. But, you know, they're very similar. So what we're saying is if it's the minimum frequency required to emit a photoelectron from the surface of a metal, then obviously we don't want any excess energy, so we don't want any energy converted, because obviously any excess energy goes into being kinetic energy, so we don't want any excess energy, so therefore we don't want any kinetic energy, so therefore the kinetic energy must equal 0. And that equals HF take the work function, just inputting our EK equals HF take theta, or theta being the work function. Now as I said, H was a constant, so it's just 6.63 times 10 to the minus 34. Now, we don't know the frequency. You can't put in this frequency because it's not the threshold frequency, because we know that frequency gives us a kinetic energy. And we don't want that. So, obviously, we can't work. Because we're trying to work out the frequency, you won't be given it and asked to work it out. Unless it's a show that question, but in that case, then, what's the point? Okay, times F. Take the work function. Now, instead of just writing the work function sign again, I would use the Joule sign. Okay. Don't use the EV sign, it's kind of tricking you into that, but don't. So you take 2.89 times 10 to the, so it's equal to 0, sorry. Take 2.89 times 10 to the minus 19. Okay, and then it's just a simple case of rearranging this. So if you want to make F the subject, F is equal to 2.89 times 10 to the minus 19 over 6.63 times 10 to the minus 34. Okay, and that's the threshold frequency. And all you need to do now is therefore just sub that into your calculator. So 2.89 times 10 to the minus 19. Sorry, 1 points. So 2.89 times 10 to the minus 19 over your 6.63 times 10 to the minus 34, or Planck's constant, which is 4.3589, etc., or 4 is basically appropriate number of significant figures. Basically, you look what else is, what the numbers they give you are rounded to, and in this case, they're rounded to 2 significant figures, so you round your answer to 2 significant figures, and that's because that's what they've rounded it to in the bits of information they've given you. So you round it to 4.4 times 10 to the 14 hertz. Okay, so that's your threshold frequency. So anything below that frequency, it won't emit any electrons. Anything above that, and it will emit photoelectrons with kinetic energy. Okay, so that's 4B part 2. We've gone to 4C. 4C part 1 says state and effect. I don't need to write anything down on the board. So we're not going to have one of them moments where I rub off everything, say pause the video a second. Right, so 4C part 2, part 1. State and explain the effect of the emitted electrons decreasing the frequency of the incident radiation while keeping the intensity constant. So state and explain the effect on the emitted electrons decreasing the frequency of the incident radiation while keeping the intensity constant. Now, we need to, this is a key thing, this is a really good question. Well, these two parts are. 4C is a really good question, I think, for photoelectrons. It's the key thing of the whole topic, is the core part that I cannot stress enough. I mean, this equation is very simple. It's just a case of subbing in numbers into a formula that you get given in the formula sheet, which is the easiest thing you ever do in physics, which generally is what most AS stuff is about. But anyway, not dismissing the AS course at all because it's very difficult. Anyway, so the key thing we need to do in this topic is focus on the difference between frequency and intensity. Now, frequency and intensity, two totally different things. Frequency, we said, is it's a formula. It's 1 over the time period. It's the number of oscillations we get per second. Okay, so that's what frequency is. Intensity is something totally different. It's the number of photons arriving per second. Now, they won't tell you that in GCSE because you don't know what photons are, but that's what intensity is. It's the number of photons arriving per second. So, if you increase the intensity, all that happens is more photons arrive per second. Now, we said the energy of a photon, E equals hf, h being a constant, therefore depends on the frequency. Now, if the frequency is changing, then therefore the energy of the photon is changing. But if the frequency stays the same, then and the intensity increases, then there's just more photons arriving with the same energy per second. So there won't be... Anyway, this question kind of highlights it. So that was just what frequency and intensity is. There's a little bit of a difference, but if you knew that already, well done. 4C part 1. State and explain the effect of emitted electrons of decreasing the frequency and the intensity is constant. So we don't need, therefore what it's saying is the number of photons arriving per second is exactly the same, but we're decreasing the frequency. Now if we're decreasing the frequency, what happens? Well, E equals hf, so the energy of the photons, as we said, h constant, etc. So the energy of the photons must be decreasing. So the same number of photons that are arriving per second, but just less of them, the photons have less energy. Now, if they have less energy, then we assume they're still emitting photons, they're not gone below the threshold frequency. So if the decrease in frequency, then the energy... So we're just asked to explain what effect this has on the emitted electron. So basically, if the electrons inside the metal are receiving less energy, then all that's happening is they're still overcoming the work function, they just have less kinetic energy. Because we said any excess energy that is occurs from them receiving the energy from the photon, any excess energy from them overcoming the work function is just transferred to the energy, kinetic energy. Now what I'm going to do is come up with a little bit of an equation here so you can understand this. Okay, so I'll rub off the frequency because we're not asked to do anything else with that. So this is the equation that I'm trying to get you to. Now this isn't necessarily physics, full-on physics equation. It's not, just to help you understand. So what it is, okay, so we know the conservation of energy can't be lost or created, etc. We're assuming this is 100% efficient. So the energy of the photon, so that's the energy in, so the energy of the photon is equal to the energy of the... So, just kind of finish off this equation, just had to nip out and, well, new video really. Well, what I've said is the energy of a photon is equal to the energy to overcome the work function plus the kinetic energy. So that's what I was kind of saying, by any excess energy to overcome the work function from the photon is transferred into kinetic. So, as I said, that's not a proper physics equation, but it's just something for you to see, to be able to understand where I keep saying this excess energy comes from. Okay, so as I said, assuming this is 100% efficient, etc, etc. Right, so the question actually asks what happens to the energy of the... Sorry, one sec, I had it up a second ago. Decreasing the frequency while keeping the intensity constant. So basically, what we're saying is that if we decrease the energy of the photon, then, so we still overcome the work function, but we just decrease the kinetic energy, so the emitted electrons have a lower kinetic energy, is essentially what we're saying. So, 4C, great. You think I would have been able to understand one of these fancy devices by now, but obviously not. Okay, so 4C part 2. State and explain the effect on the emitted electrons of doubling the intensity while keeping the frequency constant. Now, it's key to understand, so basically, we said, okay, well, frequency is the only thing that determines the energy of these photons. So if the energy is kept, if the frequency is constant, then the energy of the photons are constant, and therefore, you know, the same, any photon that is emitted will have the same kinetic energy, as we've proved by here. Right, so now that's out of the way, what the other part of the bit says, other part of the question says, well, the intensity is doubled. So make sure of that. Okay, so if the intensity is doubled, what that essentially means, as we said before, is the twice as many photons arriving per second, obviously doubling makes two. logical. I don't know why I need to say that, but you know, I don't know why I'm running away with something sometimes. Anyway, so basically there's more photons with the same energy arriving per second. So that means more of the photons can hit more of the electrons. So therefore more electrons can be emitted. Okay, so obviously because one photon can't affect several electrons, one photon affects one electron and emits one electron. That's the law of the land. Well, physics really, but anyway. So basically all we're saying is, because the intensity is double, there are twice as many photoelectrons being emitted from the surface of the metal, but their kinetic energy, because the energy depends on the frequency, and that remains constant, the energy stays the same, kinetic energy stays the same, it's just more of them with that kinetic energy. Okay, so don't get confused between intensity and frequency. I do apologise about wearing different top, as obviously a new day since halfway through the last video. I just sort of gave up. I thought, you know, I'll do some maths or something. So anyway, thanks for watching, and we'll see you in the next video. I should be wearing the same stuff.